Good afternoon, and thank you for introducing my speech. I come from Italy, the University of Cassino in Southern Lazio, and I will present this work about the numerical simulation of the interlaminar shear strength test for a glare composite. Glare laminates are is a part of a family of particular materials that are called FML, fiber metal laminates. These laminates are hybrid materials that are composed by metal and composite material, polymeric composite material. They were introduced in the 70s, 80s in the Netherlands, and they were introduced for improving the mechanical behavior of the aluminum sheets. In fact, this kind of material, compared to the composite, compared to the aluminum, presents a lower weight, and most importantly, an higher impact strength and an high fatigue resistance. So also the damage tolerance is better in this kind of material. They are used in the aeronautical field, and in particular, probably the most popular, the most known application is for the building of the panel for the fuselage of the A380 plane. That is a plane of Airbus. There are several types of FML, and in particular, we have, depending on the material involved, we have the glare, that is the material that I have studied in my work, that is based on aluminum sheets and fiberglass composite. Then there is also the aral and the caral that are based on aluminum and aramidic fiber or carbon fiber, respectively. And also by changing the metal. So if we introduce another lightweight alloy like the titanium, we have the Tigre that is an hybrid FML based on titanium and carbon, polymeric carbon. We will focus our attention on the glare. So the aim of this work is to simulate the interlaminar shear strength, so the interlaminar shear behavior of a glare laminate. And in particular, here we can observe the steps followed for the work that correspond to the outline of this presentation. First of all, there is the definition of the case study in terms of material involved, the lamination sequence, the type of test. We will see that is a 3-point bending test to determine the ILSS, but based on a short beam. And obviously, we have to define the dimension of the specimen. After, there is the presentation of the numerical model that was used for this work in terms of calculation grid, the mesh, in terms of the material models adopted, and the boundary condition considered for this work. Then the numerical model was validated through experimental activities, and so this is the presentation of the manufacturing of the specimen. We used the vacuum bagging technology, and then the experimental test that is, as I said, the 3-point bending test. Finally, there is the presentation of the obtained result in terms of the validation, so the comparison between numerical and experimental result, and the presentation also of some micrographies taken on the broken specimen. So let's start with the presentation of the case study. As I said, it's a 3-point bending test. This test was based on the American standard D2344 that is specific for polymeric materials, but can be adapted also to this kind of hybrid material. This is a 3-point bending on a short beam, and in particular, the dimension of the specimen is can be determined starting from the thickness of the specimen. So the thickness of this specimen was 5.5 millimeters. The width of the specimen must be, according to the standard, twice the thickness, so it was 11 millimeters. The length should be 6 times the thickness, so it was 33 millimeters. As concern the span distance, that is the distance between the supports for this three-point bending test, it should be no more than 4 times the thickness of the specimen. So it was 20 millimeters. Finally, the loading rate for this test was 1 millimeter per minute, and also this was defined by the standard. Then there is the presentation of the lamination sequence. In this case, the clear laminate presented three aluminum sheets, one in the center, the other two, one in the top and one in the bottom, and two layers of composite material. In this case, it was, as I said, glass fiber. We used an unidirectional S2 glass fiber with an epoxy resin. The lamination sequence for each layer of composite was a cross-ply, common cross-ply sequence with 6 plies of prepreg. Moreover, at the interface between the aluminum, at each interface between the aluminum and the glass fiber, we introduced an adhesive, a film adhesive, that was the AF 163 2K, that is a common structural adhesive used for aeronautical applications. And here, the numerical model. We used a mesh composed by brick elements for the aluminum and the composite, while the adhesive was simulated through planar elements. Concerning the material properties, the aluminum was simulated through a common isotropic elastoplastic model. Material properties are in the tables. The GFRP was simulated through an orthotropic model, an elastic model with damage routine for simulating the breakage at maximum strength. Finally, the adhesive was simulated as an interface material. In fact, we used a planar element. And here I have reported also the material properties for the adhesive too. As concerns the boundary condition, the supports and the loading nose was simulated as with rigid surfaces, with cylindrical rigid surfaces. In particular, they were placed, the two supports were placed under the specimen at the distance of 20 millimeters, as said, and blocked in space, while the loading nose was placed in the center, and at this body, a motion law of 1 millimeter per minute was attributed to simulate the test. Now, let's present the manufacturing of the specimens. As I said, the process was based on the prepreg vacuum bagging. So the first step was to cut the patches for the patches of the composite material of the prepreg, the class epoxy prepreg, the aluminum sheets, and the patches of the adhesive that was a film adhesive. These patches were stocked as said, as presented before. So we took an aluminum plate as a mold, and we started with the sequence that I have presented. So aluminum, composite, aluminum, composite, aluminum, with the adhesive at the interface. Every 3 layers of composite, we operated also a debulking step to eliminate the bubbles of air entrapped in the prepreg. After we prepared the vacuum bag, so we covered the laminate with the release agent in film with the breather fabric. We closed this stack with a vacuum bag sealed with a sealant tape, and finally we draw the vacuum. The vacuum was maintained also during the manufacturing, during the curing in the oven. This material was cured in the oven for 2 hours at more or less 130 Celsius. And finally we obtained a big laminate. This laminate was cut by using a diamond disc saw, and so we obtained this small specimen that I introduced before. Concerning the results from the 3-point bending test, we tested 3 specimens, and we can observe a quite good repeatability. Each specimen presented the same trend, composed by a first linear load increase, followed by a gradual decrease in the stiffness, so the slope of this curve. This is due to the plasticization of the aluminum, mostly, but also by a cracking of the matrix of the composite. All the trends showed a peak load at about 3,400 Newton, and this was due to the failure of the interface between the aluminum and the composite. In some cases, we continued with the loading, and we can observe a sort of increase of load. This is due to the fact that the first load drop was given by the failure of the interface, but the parts, so the laminates and the aluminum sheets, were still undamaged, or at most undamaged. This specimen behaved like a leaf spring, and for this reason we have the second load increase. Concerning the numerical model, it is reported with the dotted line, and we can see that it is more or less in accordance with the experimental data, and it tended to overestimate the load, but only of a few point percentage. As I said, I have taken also some micrographs on the failed specimen. Here we can observe on the left the first delamination, so at the interface between the aluminum and the composite. In this case, it was a light fiber tear, so the crack started at the interface, but then grow in the first layer in contact with the aluminum, and this can be related to the first load drop. While on the right we can observe a delamination in one of the laminate of the composite laminate, so the second load drop. In this case, we can observe that the crack grow between the third and the fourth composite ply, that is a ply oriented at 90 degrees with the axis of the specimen. So, to conclude, in my work, I presented a numerical model for the simulation of the interlaminar shear test in a glare composite. I tested a short beam specimen, and the results from the experimental tests are comparable to what I obtained from the numerical runs. So we can conclude that this model works quite well. The failure was due to the delamination at the interface between the aluminum and the composite, and this was the result found also with the numerical model. As a future development, we want to implement a delamination model specific for the composite to simulate the second load drop that in this case was not simulated. Thank you for your attention.